Hello everyone. In this short training video, I will explain what Simplyblock is and how it works. Simplyblock is a storage solution which is software-defined, distributed, and based on block storage interfaces. Let's look into what this means in practice. As a software-defined storage solution, Simplyblock can run on most bare metal hardware out there. This includes servers based on the x64 architecture powered by Intel or AMD processors. However, Simplyblock also runs on much smaller and less power-consuming hardware, such as RISC-based ARM processors. In addition, Simplyblock can run on almost any virtualization technology, including those used by large cloud providers and the major private cloud technologies. This includes AWS EC2, Azure Virtual Machines, Google Compute Engine, VMware, and KVM. The only requirement is the support for pass-through of NVMe devices or generally SSDs into the virtual machine. All hypervisors support features such as SR-IOV to achieve this. Now, let me explain why Simplyblock is a distributed storage solution. The data stored with Simplyblock is equally distributed across multiple cluster nodes. We use a distributed placement algorithm which works with pseudo-randomization and ensures that all nodes and all drives are equally filled. The algorithm takes the node size and performance as well as certain rules into consideration, which governs the affinity and anti-affinity of related data placement across the nodes, drives, and even possible racks, cabinets, and other failure domains. Storage nodes are organized in clusters. The beauty of our distributed data placement is the scalability of both capacity and performance within a single cluster. A single cluster can scale up to tens of storage nodes. Adding more drives and nodes will result in linear scalability of performance. A cluster rebalances itself automatically in the background when a node is added or removed or a drive fails. This is performed via migration tasks. Users can monitor migration tasks. It is possible to control how aggressively migration works compared to regular I/O in the cluster. Clusters are managed by the control plane. A single control plane can manage many clusters. A control plane itself is usually a cluster of 3 nodes. We call this a management or control plane cluster. A control plane contains the command line interface, the API endpoint for cluster management, and storage lifecycle automation such as provisioning, resizing, snapshotting, and cloning of logical volumes and the management of storage pools. It also contains the data collection and aggregation services as well as monitoring, alerting services, and log management. Those services are implemented via Prometheus, Grafana, Elasticsearch, and Graylog. Also, the control plane runs regular health monitoring services to check the state of all objects in the cluster, such as drives and nodes. It will also perform repair actions such as automated resets, restarts in case of a detected problem. We support multiple deployment topologies. When we talk about a storage node or control plane node, we actually refer to a stack of Docker containers. In a Kubernetes environment, those are implemented as pods. Now storage nodes can run together, meaning co-located with compute workloads. On bare metal servers or virtual machines, they can run as separate servers or virtual machines. A co-located deployment is also called hyperconverged. It allows to share the hardware and optionally the operating system between compute workloads and storage processing. On the other hand, the deployment onto separate nodes is called a disaggregated setup. In this scenario, the storage is connected to the host via the network. We will talk about that option in a little bit. We also support a hybrid deployment option in which local NVMe caches are combined with a disaggregated cluster. Moreover, there is an additional data service node type we support. These nodes can sit on the host or in between the host and the storage cluster and perform services such as caching, compression, and deduplication. The control plane nodes can run either on dedicated virtual machines or they can share bare metal nodes with virtual machines and other containerized workloads. Both compute and storage workloads are connected to the same control plane nodes, and the appropriate network security settings must be applied. Simplyblock uses a distributed erasure coding scheme to protect data. In distributed erasure coding, data is split into multiple chunks, and additional parity chunks are created from these chunks. Then those data and parity chunks are stored in different drives, and if possible, also on different nodes. This scheme allows us to automatically recover data chunks in case of a drive or a node failure or a full outage. In case of a temporary outage, data is recovered on the fly and new data is written to alternative nodes which are still available. In the case of a permanent failure such as a failed drive, data is permanently recovered from the failed element and distributed in the cluster. As mentioned, this works in the background and is done in any manner to rebalance the cluster across the available nodes. Erasure coding supports different schemas which are described by n plus k. In this equation, n is the number of data chunks per so-called stripe, while k is the number of parity chunks. The ratio of raw to effective storage is n plus k divided by n. For example, if n is 8 and k is 2, then the number would be 8 plus 2 divided by 8, which is 1.25. This means there is an overhead of 25%. That means 25% more raw capacity is required than effective data can be stored. Simplyblock supports numbers 1, 2, 4, and 8 for n, and numbers 0, 1, and 2 for k. It is important to note that at least n plus k plus 1 drives must be available in a cluster. Depending on the affinity rules, a cluster also requires a maximum of n plus k plus 1 nodes. In case of less strict affinity rules, clusters can also be smaller, but this impacts service availability. To tolerate 2-node outages at a time without interruption of service, at least n plus 3 nodes are required. Now, let's come back to the third part of the introduction. As the name suggests, Simplyblock primarily supports a block storage interface based on NVMe. While NVMe is a modern industry standard for high-performance drives and network block storage, a block storage interface in general allows to create any file system on top and thus provides the greatest flexibility and broadest support of options. NVMe supports connectivity over Fabric. A Fabric is either a general-purpose TCP IP-based network or a specialized network for storage, either RDMA-based or fiber channel. At the moment, the primary protocol supported by Simplyblock is NVMe over TCP, which allows us deployment on top of any general network. We also support iSCSI interfaces via data services nodes for backward compatibility and Windows. We are currently working on support for NVMe over RDMA and NVMe over fiber channel. In Simplyblock, all cluster nodes are connected to each other via NVMe over TCP, and all clients are connected to the storage cluster via NVMe over TCP as well. As this protocol is available in the Linux kernel, there is no need to install any separate software or drivers on the host that uses the storage. Also, the Linux package NVMe CLI can be used to perform host-side administration of the NVMe interface. Logical volumes and copy and write clones provisioned via Simplyblock show up as regular NVMe devices, such as dev NVMe 1 and 1 under Linux using the slblk command and can be partitioned or formatted with any file system. On top of our API, Simplyblock also provides a CSI driver for Kubernetes. When using this driver, there is no need to manually connect logical volumes as NVMe drives, format them with a file system, resize, snapshot, or clone them. All of these tasks are automated via our CSI driver. By the way, we also work on a parallel high performance and scale-out distributed storage based on Linux PNFS. But this feature still has to be released. We will keep you informed.